Well, welcome everybody, in person or on Zoom. Today we have the first of a two-part talk by Justin Ripley, who kindly accepted our invitation. Today is more of a general talk introduction, so numerical relativity and testing general relativity with gravitational waves. Justin, take it away.
Great. Thank you, Martin. Yeah, as the title says, I'll be talking about this, and Martin mentioned that this was supposed to be more discussion-based in general. So I'm trying to keep, I'll try to keep it more general, but if you want to take it in a different direction, just interrupt me and we can talk about what's particularly interesting about, what you find interesting. So the first part, we'll be talking a little bit about numerical relativity, introducing the basic concepts and a little bit of the history and major problems in the field currently. And then I'll talk a little bit more about the details about some of the more mathematical aspects of general relativity that you have to know to actually solve the Einstein equations on a computer, which will it will set us up for next week. We're just talking a little bit more about what's happening right now in testing general relativity with gravitational waves. Martin said, sort of focus on main ideas, main problems, and then the hopes and goals. So I'll try to hit these 3 points today about numerical relativity and testing general relativity, and sort of in the context of testing general relativity with gravitational waves. So first, we'll just flash the Unsigned equations because that's what numerical relativity is ultimately all about, which is solving these equations on a computer and developing the mathematical numerical techniques to solve this very complicated system of coupled partial differential equations. So Ricci tensor, R is the Ricci scalar, metric is G mu nu, Greek indices will index space-time indices, and gammas are the Christoffel symbols. Very complicated. Usually you can't solve it by hand outside of a few special cases that we all learn in the textbooks, Schwarzschild black hole and FLRW cosmologies. So when to use an R, it's whenever exact solutions or perturbation theory are not enough to tell you all the physics you want to know, and when general relativity is relevant to the dynamics. And Newtonian physics also works pretty great for a lot of astrophysical situations. What I'll be mostly focusing on is the context of generating gravitational waves for black holes or neutron star mergers, where general relativity is in the so-called strong field dynamical regime, where it's hard to make any sort of approximation about the physics beyond just solving the full Einstein equations. This being said, numerical relativity is used in a lot of other contexts as well. So you can look at the end states of space-times that have some sort of linear instability, and you want to know where do things go at late times. Usually you put them on a computer. This has mostly been used in higher dimensional space-times like black strings and anti-de Sitter space-time. You can also look at the dynamics of the early universe, inflation or bouncing models, these sort of, how does the universe get flat and homogeneous? And there, if you want to go beyond just sort of little perturbations about a expanding background, you want to use the full Einstein equations and solve that on a computer. There's been a lot of work on that. People also look at the late universe when you have galaxies forming and this sort of thing, and you can ask, well, how well does Newtonian physics describe this process, which is usually what you use, just Newton's gravitational law. But you can also try solving the full Einstein equations and ask how well things do. So this is an example of many applications of this, these sets of techniques, but I'll be focusing on the one in blue today. So testing general relativity with gravitational waves. So there's this plot everyone likes to show, which is this schematical plot of the process of you have two black holes in the universe, and they're very far apart, but they're sort of orbiting each other. As they orbit, they emit gravitational waves, so they lose energy. And as they lose energy, they in-spiral closer and closer until they merge and form one larger black hole. And it's convenient to split this process into 3 different chunks because you can use different techniques to sort of look at each chunk. The first part is the in-spiral when the black holes are very well separated, far away. There, Newtonian physics does a fairly good job, and you can sort of perturbatively correct Newtonian physics using general relativity to describe that process pretty well. The ring down, you can also use perturbation theory, where you put little perturbations around one black hole and understand the gravitational waves in this part. Sorry, this is the strain, so the measured gravitational waves by, say, LIGO or Virgo or CAGRA, these gravitational wave detectors. But during the merger phase, when the black holes are merging, it's hard to make approximations, and that's where numerical relativity comes in. So you need gravitational wave general relativity to understand this process, and you need to have theoretical modeling of this because picking out this signal from the noise is very challenging. The strain, the change in gravitational potential that you see here on Earth is extremely small, say 10 to the minus 21. So you need to have theoretical fits, theoretical templates to pick out signal from noise. And this is extremely important when you think about testing general relativity as well, which is that the templates you have are going to give you the physics you want. So if you don't model all the potential physics you might care about, you might miss that kind of characterization in the data. Okay, so any questions about that? So the merger part, which is where you use general numerical relativity, solve full Einstein equations. If you look at this graph, it's a very small portion of this whole process. Most of the signal you'll get is when black holes are very far apart, when Newtonian physics is doing an okay job and you can kind of correct it. So why do you care so much about devoting so much energy to understand this relatively short portion of the of this black hole in spiral? And from a physics perspective, you can think about what are the sort of characteristic curvature or and gravitational potentials in this process. So there are two quantities down here. C is like the Kretschmann scalar, you're some notion of space-time curvature, which we'll call C, and epsilon is some notion of gravitational potential. That's sort of Newtonian gravity, it's GM over R. This figure was made by Tessa Baker, who I think gave a talk here a while ago, but maybe she showed this, but I'll show it again because it's quite informative. When you think about what are the processes in the universe that have different curvatures and potentials, what are the different scales you're probing when you look into the universe? So say looking at white dwarfs or looking at the CMB, what are the sort of curvature scales you're looking at? And when you look at this plot, you notice that the largest curvature scales and the largest gravitational potentials you can probe that we know of, which are way up here, are looking at the merger of neutron stars and binary black holes. And where gravity is at its strongest that we know of in the universe is during the merger of black holes. So if you're thinking about looking for deviations from general relativity or testing general relativity, you want to look at scales that are very high curvature, very strong field, because that's where, using sort of effective field reasoning, which we'll get to later, that's where you expect deviations to occur. So really binary black holes and neutron stars, which sit at the very top right-hand side of these panels, and the right side is the same scale, but now I'm sort of showing where Tessa was showing where different experiments sit. That's what numerical relativity can help you probe, is this very high curvature, very high potential. So that's why you want to devote the amount of energy that has been devoted to numerical relativity to studying the merger phase. You want to get at high curvature scales. And just for comparison, in this panel, they also showed where the Event Horizon Telescope sits in terms of the kinds of tests you can do. And you can see they're looking at roughly the same potential as LIGO, but lower curvature. So it's looking at a different sort of parameter space. This is where advanced LIGO sits in terms of looking at what is gravity doing at high curvatures. You can still see the curvature is pretty small in sort of an absolute sense, but it's still, it sits above everyone else. And we can talk more about these different experiments, but really we're just going to be, the punchline of this was that that's why you care about numerical relativity, the strong field regime.
Justin, just trying to understand this plot a little more. Yeah. What the M here is associated to whatever we think is the source of the effective.
Yeah, it's sort of the mass in some volume. So yeah, what does epsilon mean for the universe is a little ambiguous, but for two black holes, you could imagine it's the mass of the system of two black holes, or let's say the smaller black hole divided by the distance between the two black holes. So
if I have like something like the memory effect, where do I put that on this graph? Where does that fit?
The memory, I guess, so thinking of, I guess, the gravitational wave itself. So like memory is, you're thinking of this as gravitational waves. I would say it's much lower down here in terms of curvature and potential, because you look at memory as being this nonlinear gravity interacting with itself, gravitational waves interacting with themselves. So, and gravitational waves are already at a very weak curvature. So I would say memory is very far down to the far left on these plots. But I guess what these plots don't capture is it's not just curvature and epsilon at a particular moment. Memory is like integrating over long time periods. So even if the curvatures are very weak, maybe this plot's not going to capture everything in terms of nonlinear gravity, because integrating over long time scales can also give you big changes, like what memory does.
Maybe a 3D plot would be nice.
A 3D plot might be nice. Yeah, that'd be more ambitious to visualize, but maybe that'll be in the works. That's a good point. Yeah, maybe time on a third axis, integration time. No. Yeah, this is also a bit misleading to say the merger gives you lots of high curvature, but the in-spiral gives you a very long time scale to integrate over. So they're giving you complementary measures of what gravity can and cannot do. Or
the curvature here is the curvature associated to the like it's the local curvature, or it's the curvature that we measure?
This is the local curvature. So the curvature near the black holes, say, or in the cosmological context, it's like this is the curvature at the last scattering surface. This is the curvature of the cosmological constant. This is the curvature like right next to the black holes when they merge. So I think what they did here is they said, what is the maximum Kretschmann scalar kind of right at the horizon of the smallest black holes that LIGO could see? That's how they define this in this plot, I believe.
Okay, thanks.
Yeah, so what we measure with gravitational waves is, way down here. It's much smaller. Okay, so it's to that point that modifications of GR, if they do exist, so here's the action for general relativity. You have this Ritchie scalar, and then let's say you wanted to add a light scalar field, let's add a new field for some reason. Like with inflation, you may look at models like this, but then modification general relativity, you get sort of higher gradients in the curvature and in the scalar fields, so higher curvature terms. These are most likely to appear. You're mostly going to see these when the curvatures are large, near small black holes, near the merger. So again, that's to go back to the point that this is why we care so much about the merger phase in terms of tests of general relativity. Okay, so that was this motivation in terms of gravitational waves. And I'll talk a little bit now about how numerical relativity works. Why was it challenging? Why has it been challenging? And then what are the current challenges? I'll be mostly talking about these more mathematical problems because as you'll see, the numerical problems are more solvable in the sense that there are many other people around the world working on solving partial differential equations on a computer, say for climate modeling or fluid modeling or engineering. So there's a lot more techniques one can look at to solve these problems, but the mathematical problems that you need to solve before you can put these things on a computer are more specific to this field. So it's been a bit more of a challenge there. There's less you can learn from other fields for this one. So now we're on the second bullet point that we're going to talk about, which is what are the main problems in numerical relativity in the past and present. So some of the biggest advances in the field over the last, say, 20 years, starting in the early 2000s, have not come from the development of purely numerical methods, but instead through advances in understanding the structure of the Einstein equations and the matter fields of equating motion, say fluids and scalar fields. The reason is because once you have your equations and you cast them into what's called the stable form, which we'll talk about, you can use these relatively standard numerical techniques that have been, say, pioneered in computational fluid dynamics. That being said, so gains in numerics have been important, and there's a lot of people working on the numerical end of things, but sort of what made this whole field possible for studying black holes has mostly been on the more math end, and that's what I'll try focusing on because that was the part that people thought might not be possible, let's say around 2000. Okay. So the idea is to solve the Einstein equations on a computer, we think of it as an initial value problem. So you set up initial conditions, it's t equals 0 slice, which we'll say is like some sigma equals 0 initial spatial slice, and then you evolve forward in time. And so this sort of is schematically showing here. And on this t equals 0 slice, you specify the metric and its first time derivative. Just like in Newtonian physics, the position and velocity of the particle. The way you can do this that people traditionally do is you take your metric g mu nu and you split it up into what's called the 3+1 decomposition, 3 spatial dimensions in one time. And you take your spatial slice, you put a normal vector n on it, and then you define some new variables called the lapse and the shift. The lapse tells you how fast time is flowing between each little delta t, and the shift is telling you how each little position on this slice is moving between delta t. And then you have this spatial metric gamma ij. So this is sort of the canonical 3+1 decomposition that everyone in numerical activity talks about in terms of splitting up. How do you split this g mu nu, this covariant equations of motion, into a space plus time, into something you can evolve in time. So you have to pick a time direction, delta t. So to have a well-posed initial value problem, to have something you can set up on initial time and evolve in time, you have to have, your solution has to exist, be unique, and also depend continuously on small changes to initial data. So if you were to take your initial time slice and just perturb things ever so slightly, your solution can't change dramatically in very small times. And this third point has been was vexing the field back in the early 2000s, late 90s, this third point here. Exist and unique people we're taking for granted, although it can be, this has actually been a challenge too sometimes, but really with point 3, that was the problem. So in order to hit those 3 points, in order to actually satisfy them, you have the two things you have to think about. So IVP was this initial value problem, set up on initial t equals 0 and evolve in time. And there are two different things people have to think about when you evolve the Einstein equations. One is, the first one is what's called the formulation. This is maybe less talked about in physics, but it's not just, it's how you write the equations of motion, how you actually, and you'll see what I mean, how you actually write the Einstein equations as a system of partial differential equations, how you define your variables. That's one thing you have to think about. And then the second thing is, how do you pick your coordinates? T, X, Y, Z. How do you choose the coordinates, which is more what the textbooks talk about. But what's a bit surprising is that different formulations, how you define your variables, different formulations of the same coordinates can lead to numerical solutions that are actually not, or are or not well posed. So you can have the same sort of coordinates, same manifold, but if you try to evolve these in time on a computer, perhaps one way of defining your variables will lead to a stable numerical evolution, but a different way of defining them will not. And that's what people sort of started figuring out in the early 2000s, or being more aware of in the numerical community. So first I'll tell you about a set of coordinates that people were thinking a lot about in the 90s that turns out not to be a great choice, because it turns out if you would perturb your initial conditions, you lead to large growth of these perturbations, and it's not well posed, which is called the so-called ADM formulation, that I showed you earlier. There's 3+1. It's called ADM because it's named after Arnowit, Deser, and Misner, who they didn't actually think of this formulation, but back in the early 60s, I think, they thought of this. They were able to define a mass and a Hamiltonian and a momentum for general relativity, and they used variables like these, and people now name it after them, this lapse and shift. So if you plug this kind of metric, you just plug this metric into your Einstein equations, R mu nu, Einstein tensor equals matter. You get a system of equations for the spatial metric gamma, alpha, beta, and what's called the extrinsic curvature, which is basically defined as the first time derivative of gamma, this first order reduction. Now, if you specify the lapse and shift algebraically, so you can think of the lapse and shift 4 degrees of freedom, and that's how you specify your coordinates. So you could say alpha is 1, beta is 0, or pick something else. If you specify these, it turns out these don't form a well-posed system. If you were to perturb your initial conditions ever so slightly, gradients grow in time, and your numerical solution won't be stable. So this is a very popular formulation in the 90s. it didn't end up working out. People were able to show this wasn't well posed, but it took a bit of effort. So yeah, that was the sort of one surprising fact from the 90s. But what people then turn to, or some people turn to, is a well-posed formulation where instead of specifying your coordinates by saying, I'll give you some algebraic expression for the lapse and the shift, say, instead, so now you think of your coordinates as being x gamma, where x gamma can be, say, t, x, y, z. It's a scalar function for each of these components. And if you say each component, say like t, set us as a wave equation. So box of that coordinate component, a box of t equals some function, h, which you're allowed to specify. And if you were to actually expand this out, you say, okay, let's specify the trace of the Christoffel symbols, this quantity here equals some function. Then if you plug this into the Unsigned equations, they look more like this, where now the metric you see has a wave equation. And this does have a well-posed initial value problem. And this was proven back in the 80s, although really an earlier version of this where h is 0 was proven by Choquet-Brouat back in the 50s, when she proved that general relativity does have a well-posed initial value formulation in some set of coordinates. But if you make h arbitrary, in principle, you can get any coordinates you want. So with this formulation, the claim people have made, although it hasn't been proven in blue, is that with any choice of coordinates you want, you can specify some h, and the Unsigned equations will have a well-posed initial value formulation in these coordinates. So just to give you these two flip sides, in the earlier formulation, I gave you no coordinate choice was going to work for you. And in this formulation, supposedly every coordinate choice can. So that was the realization people made in the early 2000s that it's not just how you choose coordinates, but it's how you choose to specify those coordinates. Here you give them a wave equation.
Justin?
Yes. Sorry, can I ask a question?
Yeah, there's a question. Enrique, go ahead.
Yeah, so I'm just wondering, this harmonic condition, it reminds me a lot of the similar Lorentz gauge in electrodynamics. Yeah. And there we know that that's not a complete gauge fixing unless you impose some boundary or asymptotic conditions and so on. So here I'm also wondering, is there other information that you're
right? Yeah, there
imagining here implicit asymptotically or stuff?
You're right. Yeah, I think that's a good point. You think about boundary conditions as well. So, so if you have a black hole, so the idea of these, you're right. So this is just like, this is really the sort of the nonlinear generalization of the Lorentz gauge. And if you think of if you think of gravitational perturbation theory in books, they talk sometimes about like the Donder gauge and these things, and that's sort of the linearized version of this, with h being equal to 0. And you do need to specify boundary conditions, because the wave equations don't have well-posed initial value, aren't well-posed unless you specify boundary conditions. So if you have black holes, the boundary conditions are, you don't put boundary conditions because everything falls into black holes. So that's okay. And far away from everything, usually you say, well, if it's a cosmological space-time, then you say asymptotically go to, say, like a de Sitter cosmology or FLRW cosmology. And if we're asymptotically flat, then we say asymptotically flat boundary conditions, which, so there are different ways of specifying asymptotically flat boundary conditions. And in fact, there are boundary conditions that you can specify that aren't quite asymptotically flat, and it actually can kind of mess up things for you. So you do have to be careful about boundary conditions. But,
right, and the conditions that you're specifying are on the x gamma, are on the coordinates themselves.
Yeah, so you can think of x gamma as, it's not a vector, it's like a scalar.
Yeah,
tx.
right, sure.
Exactly.
Yeah. Okay, and just so a very quick question. You mentioned that the previous way of specifying conditions on the lapse and shift is no longer deemed well posed. Are you going to say a little bit more about that, or
so I guess I should say, and when you write the Einstein equations this way, if you specify these algebraically, they're not well posed. But if you specify, there actually are ways of fixing this here, ADM. And actually, I would say most people. So maybe I'm not being fair. This is the sort of formulation that I use and people I know use. Most people actually use a modification of this formalism it's called BSSN. It's acronyms for Baumgart, Shapiro, Shibata, Nakamura. And so there's a way of actually rewriting this. And also if you specify these not algebraically, but if you give them, say, I'll set my gauge by saying not A equals 1, but DTA equals K, the trace of this, or something like this. Then this becomes well posed. Yeah. So if you give these sort of wave-like equations or transport-like equations, then these are okay. So yeah, I'll flash up the other formulations. This is just one, and it's actually not even the most popular one, but I think it's the easiest to understand why it works, because you can see here that it's like a wave equation for the metric and a wave equation for the coordinates. Everything's a wave equation, and then you can see why it works. If you were to write the BSSN equations, it would take me 2 slides. They're awful, but they're also well posed, and they have various advantages that people like.
Justin,
great.
We have another question in the room.
Yeah, so I come from hydrodynamics or gas dynamics. It's a nonlinear theory, but you can write the equations very simply in conservative form. Box some tensor equal to maybe some source terms, and it works fine on the computer, right? Once you have this conservative form, you can talk in terms of densities of quantities, fluxes of quantities, use the conservation laws, evolve in 3+1 space, and we do it all fine. So what is it that makes the gravity problem so much harder? Is it just that it's more dimensions? I mean, more equations? Is it that you're solving for both coordinates and densities? Or is there something really fundamentally more complicated?
I think it does come down to, you have coordinate, there's this diffeomorphism, coordinate invariance, and general relativity. So in fluid mechanics, so I mean, you can talk about primitive variables versus conservative variables and this sort of thing, but I think the symmetries of fluids, they do exist, but they're less, like, I guess, maybe I'm wrong. The general relativity has like local symmetries. The coordinates can sort of change from place to place. And I would say that's the main challenge, is thinking that is remembering that in general relativity, the coordinates themselves have to be evolved in time. And in this formulation, so the coordinates themselves have dynamics. So in this formulation here, it's not well posed. You have things that will blow up small perturbations. But what's blowing up is not physical quantities. You never have the physical solution. It doesn't depend on coordinates or formulation, but it's these unphysical quantities here. The coordinates themselves and what's called the constraint violation. How well are you satisfying what's called the constraint equations? Those can also blow up, and those do depend. And I think in the fluid equations, the velocity, all these things it's all physical in some sense. I'm gonna say that everything is physical in fluids for the most part. So long as the physics is well posed, the equations should also probably work for the most part. But in general relativity, you have lots of non-physical things to deal with, and it's a big annoyance, but it can destroy your simulation.
Justin, when you say not well posed in this context, you mean number 3, right?
Yes.
Okay.
Well, actually, I'll say in physics literature, once people hit on this idea that you need what's called strong hyperbolicity, everyone starts proving strongly hyperbolic formulations in general relativity, which is point 3. Small perturbations lead to small changes. No one really has written that much on 1 and 2. Although actually, I didn't put in this slides because I didn't want to have the whole talk be taken up by like lots of, I wanted to stay as big pictures as I could. But if you think about the initial value, the initial conditions, which you have to solve, those constraint equations can have multiple solutions depending on how you formulate things. So you can actually find multiple solutions to the Einstein equations sometimes, especially when you think about the constraint equations. So like elliptic type problems.
What's hard about that, there needs to be some untangling in uniqueness, right? Because of course, uniqueness is only up to diffeomorphisms.
Yeah.
And when you fix, say, alpha, beta, establishing uniqueness is tricky because you're not aiming for something that's actually unique. You're aiming for something that's unique up to some, right? Up to some. So assessing whether or not number 2 fails or works depends on the gauge choices you make, and depends on what you set your defining equations to be for your coordinates. So for instance, coming back to Enrique's point, or at least what I think Enrique was talking about, for the box x equals h of, right? This is a choice, but there's lots of freedom. There's lots of things that will satisfy this. So if I change x by something which gives you 0 when it's hit by a box, that would give me the same big H on the right-hand side.
Yeah.
So uniqueness will always have to be modulo the subtleties of your setting up of the problem, which renders the analysis, I think, kind of harder. But if number 3 fails anyway, then I think your coordinates should go in the bin, and you should look for something else.
Yeah, I would say, from the physics perspective, people like to assume all 3, and then they only want to tackle any of these if one of them starts failing. So 3 was giving people problems, they started attacking 3. 2 can give problems, but people sort of, what you do then is, if you don't have a unique solution, is you start with an initial guess for a solution that's very close to what you think it, quote, should be. And then you hope that when you correct for that solution to give you the full solution, by sort of solving Einstein equations iteratively, then you actually reach the one you want. But it's not, coordinate, and as you said, like the physics shouldn't change. The physics should be unique. So, we can talk more about that later, maybe at the end. But the problem is with some of these formulations that have non-unique solutions is that you're doing all these sort of nonlinear field redefinitions. And when you're doing nonlinear things, sometimes it's like taking a square root of a number. There's plus and minus. You give yourself multiple solutions, even maybe when there shouldn't be. So there's issues with that.
I should definitely let you go on, but there's the blue sentence. I would like you to say more about that at some point. And then Enrique has a hand up as well. But Enrique, is this a quick one? Because if it's a quick one, we can do it. If not, we
okay, I'll let him go. It's just about, very quick, it's just about if these conditions always have a physical interpretation. For example, the CMC condition has an interpretation of choosing simultaneity surfaces so that everyone measures the same Hubble expansion. And I was wondering if all these conditions have some such physical interpretation as well. But this can
that's great, because actually they don't, and that's why people don't like using these coordinates. It's because people don't quite know how to interpret things. And when you use lapse and shift and extrinsic curvature and things, you can say, okay, there's a physical interpretation you can sometimes get. I'm saying the volumes of my boxes can't change, or I'm minimizing distortions. This, people aren't always so sure, and that makes people nervous. But you can also just say, I pick an H that works, and then if it works, I'm happy. But yeah, it makes people nervous, and that's why only a few people use this. Although actually, one of the biggest codes right now that does most of the simulations for LIGO uses this formulation spec. So the Caltech Cornell group uses this, a variant of this, and they're the ones that are making those high quality numerical relativity waveforms that LIGO uses for a lot of their data analysis. Well, at least they make the most. So yeah, I mentioned so general harmonic is actually a lot more other formulations. There are more formulations out there than there are codes. And they all have lots of complicated acronyms named after the people who invented them. I'm giving you the most famous ones that people actually use. So BSSN, which is named after Shibata, Nakamura, and Baumgart Shapiro, they're from the 90s. And then there's Ohara and Kojima added some things, and it's called BSSN OK. There's also a Bona-Massot slicing. And then there's something called CCZ4, which is I forget what this stands for. The Z, I think, doesn't mean anything. 4 means 4 dimensions. Conformal, there's a lot of acronyms for a lot of these formulations, and the list goes on. I just want to give you a sense that this is definitely not the only one that works. There are many more, and they have different advantages. Maybe we can talk about if you're curious, but they have different advantages. One of them being you can sort of more physically specify your coordinates. So one more thing I'll try to, I guess I have 740, so just very briefly is that, so well-posedness is not quite enough. If you can have well-posed initial formulation, which means that small perturbations don't lead to sort of infinitely fast growths of different terms, but you could still have things grow exponentially, and that's continuous. Exponential functions are continuous, but it's still a big problem for you. And there's something called constraint violations that need to be damped. I was debating whether I should put this in or not, but it's something people worry about, which is that, so like with generalized harmonic, I said gamma equals h. You specify this on the initial time slice analytically, it should be 0. But we're on a computer, we're approximating things, nothing is exactly 0. You want things to stay close to 0 though. So you define this thing C, which should be 0, but it's not going to be exactly. And you want this thing C to be close to 0 at all times. And it turns out it can grow exponentially if you don't modify your equations yet further in a way. And the way you do that is you add things that are formally 0 to your equations of motion. So if everything was exact, it wouldn't change the solution, but if it's not exact, it modifies it, and what you do is you add these terms that should be 0 in such a way that they actually drive things, this C to 0. So this constraint surface that should be 0, C should be 0. You add terms such that it sort of is damped towards that constraint surface. It's called constraint damping. And it was sort of pioneered by these two people. But now I'm fearing maybe I'm getting too much into the weeds, but you can tell me more, ask me more if you want. The point is there are other things you have to worry about in addition to well-posedness and formulations. And all this is to give you a sense that G mu nu equals T mu nu. It works when you're solving things by hand. But when you want to put things on a computer and things are inexact, you have to worry about a lot more issues. And it depends actually how you write the equations of motion will make or break your simulation.
We have a hand up
way of saying this. Yeah, please.
How do you know if the term is going to blow up? I mean, you can test it by following it out a certain amount in time, but how do you know that you've gone out far enough to know whether it's blowing up?
So what you do is you take this guy here, this vector, and let's say you take some norm over some volume. So you just sort of integrate, say, CT over some volume. And then you just sort of, you watch that over time. So as your simulation is running, you're just sort of looking, does CT increase over time or decrease? So you plot the constraint violation. And if it starts growing, you start worrying. But if it doesn't, you're okay. And actually, really, it's more of a problem-specific issue. You don't want C. It can grow. It just can't grow so fast that it becomes very large by the end of your simulation. So you just don't want. You can think of this as sort of quantifying your error. And error can grow. It just can't grow so fast that it sort of overwhelms the accuracy of your simulation. And then what you do, what's even more important for numerics is you run this at different resolutions, and you want to make sure that C is going to 0 as you increase whatever numerical discretization of your equations is. As you increase your discretization resolution, this goes down. But so it's really sort of like you watch it. A priori, this doesn't have to work. So there's sort of like semi-analytic. You sort of perturb these equations over flat space-time, and you see this should drive C to 0. Does that work for black holes? Well, you have these free parameters, kappa and rho, and you tune them. They are negative, I think. You make them negative, and you make them sufficiently large that C doesn't grow too much in your simulation. But it really is like an empirical sort of thing. At this point, you're sort of like treating, once you write the equations like this, you kind of treat your simulation as like an experiment, and you start tuning parameters to make it run. Yeah, a priori, you don't know. But you can always watch it. You can plot it. Yeah, so I should say, I basically give you a very biased account. This is what, so it's a little bit of history in numerical relativity. People were trying to collide black holes in the late 90s, early 2000s. All their simulations were blowing up, and people were starting to get pretty worried. They were worried that LIGO was going to become functional before we had gravitational wave templates for the merger phase, because numerical relativity was struggling. And what Franz Pretorius did, which surprised people and made them very happy, was that he basically solved the Unsigned equations using this generalized harmonic formulation. He used the constraint damping I showed you, and he was able to get two black holes to collide. Actually, I should just show you the picture at the end. Able to get them to collide, and he used this formulation. That's why I'm showing you this one. It was the first formulation, the first sort of set of tricks that got two black holes to actually collide. Once Franz was able to do this, and I think it was 2002, several other groups using different methods were able to also collide black holes within about 6 to 10 months. And people had a lot of hope. And I think part of it was like having hope that this should work, gave people that extra energy to do it. So you're seeing that the first one that worked, but now there's many more. And now, of course, colliding black holes is something that people do all the time. If undergraduates can do it, graduate students, when they start the PhD, it's like an example you always do. It's become much more standard. But it is a lot of experiment. Numerics is like a mixture of experiment and math.
Justin, just to let you know, you've got 15 minutes left. I don't know how much you want to get through.
I'm going to race through some of these pieces because it's more standard.
Yeah, if
the general thing, or if you have other questions you want to take it elsewhere. I mean, this is more standard.
Well, so
here.
I think it depends what you had in mind for what you wanted to talk about. If you were going to lead us through some of the details of the things that you've mentioned, I can see a conceptual problem in my mind that's just screaming, and so I thinking maybe that you can lead us through that.
Yeah.
So and in particular in relation to what you just said. So when you say people collide black holes, to me, that's a dream, right? As a mathematician, we want to understand how these things work, and there's absolutely no way of doing that.
The picture.
So yeah, you'll have to explain to us what's going on.
I'll explain the picture, but it's nice.
But
when we're talking.
But the basic issue I see is that, as you know, a black hole is usually understood to be an event horizon, and that assumes global evolution. So I have a scry plus, etc. So now we're thinking of a 3+1 type snapshot. So how do I first of all delineate the boundary of the black hole in this context of 3+1?
Yeah.
And the second thing is your coordinate choices somehow have to reflect have to take on some value on these boundaries, right? Because you're not trying to simulate what happens inside.
Yeah.
And so I see that causing an enormous amount of complication on top of everything that you've already said.
Yeah.
So is that something you were going to talk about or not?
I wasn't, but I can, and this picture is going to help us.
It's up to you. If you don't want to talk about it, that's fine. We can talk about it next time if you had your plan and
No. So I mean, the rest of this was a little bit of this computer stuff, but the big point is that you can, when you have these mathematical issues solved, you can use sort of more quote standard techniques, which is have been used in say computational fluid dynamics to solve these equations on supercomputers. So here's a supercomputer. You got rows and rows of computers. This is the picture of the one I've mostly used. It's in Quebec. It's French for narwhal whale. But that's sort of the punchline of that. And I wasn't quite sure what the interest would be, but I think we may as well, since we don't have, I know there's another talk coming, so maybe we can talk about this first. So this picture here, this is actually one of, so when I said Franz, he collided two black holes, and there are other groups that followed him. This is one of the pictures from one of those first papers. what is the picture? So these little dots here are like tracing out the trajectories of two black holes. So you got two black holes. These little circles here are the apparent horizons of the two black holes. So they're not event horizons, but they're apparent horizons. So you do on each spatial time slice, you look for null rays that are ingoing, like you pull pulse of light ray, they fall back in on themselves. That's the inside the apparent horizon. It's a coordinate dependent concept, but you know apparent horizons should sit inside apparent horizons. So the black hole probably looks something like this. You start with two black holes and you can see they kind of grow a little bit. That's because of coordinate choice. It's like a coordinate dependent growth of the apparent horizon. It's not physical. So the first question, how do you find the black holes, is you have to search for apparent horizons through what's called apparent horizon finders. You sort of define some set of null directions where light goes, and then you look for the places where all the light rays are sort of ingoing in some sort of defined sense. That's how people find them. And then what happens inside the black hole, there are two main approaches. So one is that you say, well, everything is ingoing inside the black hole. Everything's falling inside towards the center. So you could just say, I don't really care what happens in the middle of the black hole. I just cut out from my domain the inside, black hole excision. You just excise from the inside of the black hole, and you don't evolve. So at that excision boundary, you know how to evolve. You know what the boundary conditions are, because there are no boundary conditions. Things are all just falling into the black hole. Some codes do this, like Franz's code and others. And then other people, which is what this simulation is showing, is they use a very particularly fine-tuned set of coordinates, this BSSN formulation called puncture coordinates, where you actually evolve the entire space-time right down to the singularity, like r equals 0. And but what you do is you choose coordinates such that, maybe I should have put a Penrose diagram here. I didn't put this in the slides, but the idea is that there's like this Einstein-Rosen bridge between black holes, that sort of fake thing they talk about in textbooks where you go from one universe to another. Well, actually, you can actually, in black hole, in numerics, you can actually kind of simulate this by choosing coordinates that kind of asymptote to the Einstein-Rosen bridge, which means you're kind of avoiding curvature singularities. You just kind of go to this throat, and you define coordinates such that the center is actually sort of the bridge to that wormhole sort of thing. So there's no curvature blow up in your solution, modulo some like 1 over r things, which you can analytically factor out. And so you can actually evolve the interior of black holes. That's called puncture type evolution. It's the most popular kind of evolution, even though it sounds really complicated. It's actually quite popular because you don't have to do this sort of excision thing, which people find a little bit tricky to make work. And that's what these BSSN other kinds can do. And that's what this simulation is showing. This is like the center of this puncture trajectory, they call it, where the Einstein-Rosen, it's not actually an Einstein-Rosen bridge, it's more like they call it a trumpet-like geometry. It's been studied by lots of people who find this kind of interesting. But you can evolve the whole space-time. So that's sort of like 2 answers to your 2 questions in a rapid fire. Unfortunately, no.
Wait a minute. The Rosen bridge, are you going through the bridge, or are you just stopping at the bridge? Or is it asymptotic to?
It's asymptotic to the bridge. So I really should have a Penrose diagram. Maybe I can show it. I can show you a paper. I can link you to a paper that has a really nice Penrose diagram of this, where it's like your coordinates are kind of asymptoting to it, but you never actually reach it. Because actually your lapse, your time dt between each physical time is also what's called, the lapse is collapsing. So actually time is sort of freezing out at the puncture as well. So time is freezing out, you're approaching this wormhole, but you never actually reach a wormhole. It's more like a trumpet, like geometry.
So you just choose coordinates that blow up in the spatial direction, if you will, on approach of the wormhole, which guarees that essentially you don't have to care about the two-ended data. You don't have to care about going through the other event horizon.
Yeah. And so your numerical resolution in these regions is horrible because things are blowing up. But whatever horrible things that are happening to your resolution and accuracy are happening inside a black hole. And it turns out that all this error is sort of That is also what's important about sort of specifying dynamical gauge conditions. Is so all of your errors also are following wave-like equations, and then they can't escape the black hole. So the sort of the logic of all of this is that you can almost do whatever you want inside a black hole because they can't escape. So you can make horrible numerical error and do things like punctures or excision because it's all trapped, which means you have to make sure you're actually doing this all inside the black hole. That's why finding apparent horizons is quite important. You can also find event horizons, but that's harder. Event horizons are defined with respect to the future. And there you have to the thing everyone does is if you want to find event horizons is you take your solution way out to the future, you evolve for a long time, you start with some little light rays, then you integrate backwards in time. And then because the event horizon is kind of an unstable surface for light rays to the future, they kind of either fall into the black hole or you fly away. If you evolve backwards in time, light rays converge to the horizon. So then you kind of evolve your simulation backwards, and then you can find event horizons. You evolve your geodesic equations.
If I give you, is the field sufficiently mature that I can ask you for a simulation of say two mass equal 1 located at say 1 light year apart, whatever. I ask you to run that. You give them maybe a bit of angular momentum with respect to some centralized coordinate system. Is the field sufficiently mature that you can give me a movie, which is foliation of the evolution, such that you can trace on each of the snapshots the intersection of the event horizon with this slice, and then show me how the event horizon forms, how it evolves?
Absolutely. So actually, yeah, and talk about, but I'm flashing some textbooks, so it is in fact, it's quite mature now in the sense that there's some well-established textbooks, which I also put here. In fact, those kinds of movies where you have the event horizon on each slice, for simple simulations like two black holes colliding to sort of head on, there's actually some famous pictures from the 90s even of that. For binaries, you can also do that as well. Do
the surfaces appear? I'm guessing it's not continuous, right? The surfaces just appear, right? If you have two apparent horizons that get closer together, there's going to come a point where actually an apparent horizon is going to form around that system without being a continuous opening up of the apparent horizons into a bigger one. You see that too?
So there's, I guess there's, so I was saying when two things. So are you talking about when, say Oppenheimer collapse, where there's no horizon and then there is one, or?
Yeah, I mean, just take two soap bubbles, bring them closer together. Yeah. There's going to come a point where the minimizer of those two systems is no longer the two soap bubbles, but a bigger bubble which contains both of those regions. But that appears out of nowhere. That's a jump out of nowhere. It just appears.
So for the apparent horizons, that's what's happening here. Is you have these two black holes, these two orbs, and then at some point they form this peanut, and that's the collective apparent horizon.
And you can see that at the level of the event horizon.
It happens. Yeah, the apparent horizon, it happens immediately.
Yeah.
That's and it's nice. Actually when you think of, so actually for black hole excision, that's super important because you have to excise inside the apparent horizon. So you want to make sure before you excise the big black hole, you find the apparent horizon for the big black hole. So it's
Can I clarify this point? I thought you have these two bubbles coming, and then a nose kind of stretches out, and they meet. And that, in fact, is what becomes the new single horizon, which is different from what Martin is saying. Martin is saying these two guys come and some other surface forms independently outside. Is it that?
So I think apparent horizons will form sort of spontaneously, but event horizons, if you were to follow the event horizons, you get what's called these pants pictures where you have two pants legs, which are the two black holes, and then they connect continuously. And there's these sort of pants pictures they have where it's two black hole event horizons and then they continuously merge. So event horizons are going to be sort of a continuous thing, but the apparent horizons are more of this jump.
Okay, thank you.
Interesting.
And their coordinate, so you can see how like the coordinates really do change a lot here. So it's so yeah, I mentioned, I guess I didn't talk about how to find black holes. Maybe I should have put that in there. So actually, also you asked, is it mature enough to find angular radiation? People now are talking about, so to get gravitational radiation accurately, you want to make sure you're in the center of mass frame. And people are now talking about getting, to 3 or 4 decimal places in terms of determining the center of mass frame of your system and the angular momentum and the memory. This is all of what's called the, let me get to the end here. We don't talk about this. I'll talk about this next week. Did I mention the code? Yeah, sorry. I put it, it's never a problem. Did I list all the codes? Yeah, here it is. There's tons of codes. They have many names.
Wait,
Spec
Justin
is the one that can do those really accurate things. Yeah.
Justin, I'm still yeah, no, actually we're done. I really want to continue this conversation, in particular about the event horizon thing that Ramesh was saying. But I think we're gonna have to wrap up.
Yeah, that's fine.
So let's give Justin a round of applause.
Yeah.
That was a beautiful talk. We'll see you next week, and maybe try and leave some time next week for some debates and some questions.
Yes, I'll try to shorten it a little bit.
No. That was great. That was great, Justin. Thank you so much. Yeah. See you all very soon.
Yeah, I'll see you guys next week then. Thank you. Bye.
Thank you. That's so much.